name is Jakub and I would like you to present MedVoxelHD, the software for fast and detailed evaluation of the segmentation algorithms in medical imaging domain. So let's start. First of all, I would like to show you how to configure the environment. So the environment is in the dev container folder, and we have the dev container JSON file and Docker file. In order to simplify it as much as possible, you can use the remote development extension of the Visual Studio Code. It would recognize the dev container folder and load everything automatically. The only thing that you need to do is to supply the path to the CT-org dataset or any other dataset that you would like to use for testing, and the rest would be happening automatically. Of course, you can also just look at the Docker file as what is used and adapt it to your needs. So now, as we already have the environment set up, let's get to the example of how we can use it. So first, we open the case analysis Jupyter notebook that is present in the repository. We load all of the libraries and interface HD, that is the Python file with the interface to the CUDA C++ functions. Then we have some helper functions that will be used just for the presentation of the results. We are here pre-processing, standardizing spacing, standardizing orientation, so very classic pipeline for the medical segmentation domain. And we simulate the algorithm output by dilatation of the gold standard mask. That way, the results would be very easy to interpret in the later visualizations. So, how we use it? When we have the tensors as booleans presented, so labeled bool tensor A and label bool tensor B in this case, we are ready to go. So as you see, here are the four functions that we are using: get Hausdorff distance, get Hausdorff distance 3D rest, get Hausdorff distance full rest list, and get average Hausdorff distance. All of them are very fast, far faster, at least order of magnitude faster than any other implementation. And they can supply all a bit different kind of information. As you can see, all of them will accept three arguments, labeled bool tensor A and B, so that would be the gold standard tensor and the tensor that will be output of our algorithm that we would like to compare. The order does not matter. And robustness percent. What does the robustness percent mean? It means that we would like to ignore some percent of the most distant Hausdorff distant voxel. Yes? So for example, if we put the robustness percent in 0.95, it means that we would ignore the 5% of the highest per voxel Hausdorff distances. Okay? So, and this generally is used in order to increase the robustness. Yes? So the smaller the percent, the bigger the robustness for this. And I will show you this on the in this example. So for example, if we put 1, 0, we get the classical definition of the Hausdorff distance point by get Hausdorff distance, and it will be 45. It means that the farthest away the voxel that is present in this segmentation is 45 voxels from the other mask. Yes. However, if you look at this histogram is presented from the array that is get Hausdorff distance full rest list, and it shows what are the distances of the voxels from the one mask to the other. Most voxels are very close, yes, 1 voxel, 2 voxels from the original distance. But there are several single voxels that are quite far away. These are basically for our use case outliers. So in order to avoid dealing with these outliers, we can reduce the robustness percent, yes, even to 0.9, for example. So we would catch 90% of it, and you can see that the classic HADA changes to 8 and average to 199. And this is far better representation of what we see, at least for most use cases. But this is just a histogram. We can do far more than this. We can also get the 3D result and display it. So now we can see the difference between those two masks. As we already explained, we have the one mask that is gold standard of the liver in this case, and the other that is dilatation of it. And we see that in those two areas, the Hausdorff distance per voxel is the highest. This is the very simple case, but of course in real life scenario, this would show us very clearly with what issue the algorithm has. For example, in my experience, I had the algorithms for the liver segmentation. They frequently miss the liver with the spleen. And we would see that the most issue with the segmentation is in that case with the spleen. The other problem that is also very clearly seen in such cases is that we never have ideal segmentation mask created by the radiologist. This is basically impossible to do it perfectly because where the organ ends or starts is not always so clear cut, at least not in all of the places. Hence, some small changes from the gold standard to the algorithm output, if they are very close to the gold standard mask, are not so important. However, still, this is just a 2D representation of 3D object. And we cannot see exactly why here and here is the biggest problem. In order to represent it even better, we can save the images and show it in some image viewer, for example, 3D slicer. 3D slicer, in this case, we see three-dimensional representations of the tensors that I had already shown. So this is a dilated image, the image of the dilated gold standard mass of the liver. This is the original gold standard mass of the liver, and this is the difference. So this is the Hausdorff distance. As you can see here also, on the left and on the right, you have the highest values, particularly here on the apex. Why is it so? Let's look at the images. If we look, for example, at the hilum, so in this area, the change of dilatation would not lead to very big changes in the Hausdorff distance because there is a lot of irregularities in this. So by dilating, we mainly smoothen out those irregularities. We always have some voxel in some area that is close to the dilated image, yes? Because something sticks out. The situation is different here. When we have the very peak of the liver in this area, we, at least in this 3D representation of it, we see that there is nothing up, nothing down, nothing back, nothing in anterior. We have only some voxels to the left. So any dilatation in this direction would lead to the situation that we do not have anything close in the 3D distance. Hence, this is the situation that we see. So we see that those voxels are far more distant than any other. And voxels in the hilum are very close to some other voxel. Okay? Okay. This is everything that I want to show you, so thank you very much. In case of any issues with using this software tool, please open the issue on the GitHub repository or contact me on the LinkedIn and I would try to resolve it. So thank you very much for listening to me and happy coding.